So, day two, let's start the day two with the problem number one, that is check completeness of a binary tree. Given the root of a binary tree, determine if it is complete binary tree. In a complete binary tree, every level except last possible is completely filled, and all nodes in that last level are as far left as possible. It can have between 1 and 2 to power h nodes inclusive at the last level h. So we are given a complete binary tree. So we have to check a tree whether it's complete binary tree or not. We are having nodes. So let's see the first example. We have root node as 1. It has children left and right, so it's complete level. And then we move down to 2. Then we have 4 and 5 here. It is also complete level. Now moving to third node, it has 6 as a left child. Every level before the last is full, i.e. levels with node values 1, 2 and 3. All nodes in the last level are as far left as possible. So since 3 is not having a right child, we can say it is a complete binary tree because it is as far left as possible. So this 6 node is not missing in this particular tree. So that's why it's a complete binary tree. Now moving on to the second example, it's a similar example, but the 6 node is missing out in this particular question. As you can see, it's 1, 2, 3, 4, and 5, but 6 is missing out. So since the 6 is missing out, the node with the value 7 isn't as far left as possible because this 7 should be here. If the 7 was here, then it could have been a possible answer. So let's see what we can do for this particular question. We have a tree in which there are nodes, and every node has suppose two children. No, suppose two children. It must have two children, and if it does not have two children and it is a last node, then that last node should be as left as possible. So this tree, this level is valid, this level is valid, this level is also valid. So this level is valid, this level is valid, this level is valid. So there is a case where I have this, then there's this, and then there are two more children. These two are there, but just there is this right child. This left child is missing in this particular case. Now, if I start a traversal at each level, go level by level, and ask the level whether it has this particular complete structure or not. This level also has a complete structure. Now this level does not have a complete structure because this particular node is missing. So what I can do is, for each level I create a vector, and in that vector, if I store the nodes of that level, so I have a vector, and that vector I store the nodes of that level, and then after traversing each level, that vector is filled, and then I traverse that vector once, and if in that vector I encounter no null value, then it's well and good. And if I encounter a null value, then there should be no further node from that null value. Because see, this is a case. I have a value for this node, okay, that's well and good. I have a value for this node, that is well and good. But as soon as I come down to this node, it pushes null here. Now, when I move forward, there's a node that is existing here. It should not exist here because null has already been seen. So that is the kind of scenario that I am thinking of building, because there should be no further nodes in that particular case. Now, but there's also issue that we need to deal with is that there could be a case. Let's see if there's a case, something like this. We have this particular node, and there's this node that has only left child, but these node also have children. So technically it's a false case because this particular node should have both children because it's not the last level. This is the last level. So only this level should be valid. So in that particular scenario, what I'm thinking is that if I am marking only go by level, so this level will become true, and then when I go here, this level will be also true because this is a farthest left that is possible for this particular case, and this level will be also true because this is the farthest left for this particular case. So that will become an issue. So if in that case scenario, what I'm thinking is that What I can do, just create a queue in the VFS traversal. I will be doing a queue. Every time I push a node in the queue, then I check whether the particular node is null or not. So if I have a queue, I push my root node, and when I push my root node, and when I want to go to the next level, I just need to pop this node and push these two nodes. But for some reason, if this node is null, then null will be pushed in the queue, and this particular node is will be pushed. But still, that how will manage that particular case of true and false, because if this is not array wise. Because if the original idea was to store all the nodes in a vector of that particular level and check level by level. But the issue is that there could be a case shown this similar case. So to solve that kind of particular solution, what we need to do is what if we have a flag for this node? I mean, every time I encounter a null node, or first time when I encounter the null node, I will set this flag as true. Now, apart from this flag, after this flag, there should be no node. So, if the flag is encountered once, there should be no node. So here, as soon as I encounter the flag, it is a null node. So I turn my flag true, and when I come down to this level, and they will see that particularly the flag is already true, it will break the loop out, and I will just return false, because that would be a case where the particular solution will break out. So I think I can just write a simple BFS for this particular solution. I just need to point out the flag value for this question. So it's a queue. Let's start working on this. E just need tree node. What is the name of the queue that I should put? Let's name it as QUB. QUB. Now I need to push my root node in this particular case. Now after I push this, now I need flag. Flag will be initially false. False. Then what I will do is just do a simple BFS for this case. It would be very simple. Size two. Now I will for this Subtrees, or just q dot pop. Now if this particular node out is well and good, but what if this node was null? So if my top is null, what I need to do is flag will turn to true. Now since my flag is true, that means I have encountered a null node, and there shall be no new nodes after this. So when I have encountered a null node, there should be no further nodes after this particular node. That's what my working is based on. Now there is this else case. I will just check if my flag was true in past. Then I just need to do is return false, because I am breaking my condition. So a new node is encountered after the node. Now, if this condition is not true, what I need to do is q dot push top left and q dot push top dash right. Now, in this particular case, we are not checking that whether left exists or not, or right exists or not, because our whole case is based on whether left exists or not and life right exists or not. So that particular checking part is not here. After I have completed this, I will just return true. So it's a easy problem, I would say. If you have basic concept of the level order traversal cleared or BFS traversal cleared, it would be a pretty easy question to solve, I guess. See, okay, compilation error. Okay, there's empty. We have tried wrong. Is there any more error? Let's have this. Okay, let's see. Q dot side. Okay, let's type Q. Q, EQ. Let's try to submit this. Okay, so we were able to solve this particular problem. It was an easy problem. So I guess it was no some brain juggling kind of problem. So that's an easy case. Now what we'll move down to is our second problem. Binary search tree to greater sum, right? We have binary search tree and we have to convert it to greater sum tree. So before that, let's just clear this particular screen. Now let's see this particular problem. Given the root of a binary search tree, convert it to a greater tree such that every key of the original BST is chained to the original key plus the sum of all greater keys that the original key in the BST. As a reminder, a binary search tree is a tree that satisfies this condition. We all know what a binary search tree is. So there's this particular nodes and all these kind of values that are present, and for every node I need to find the greater value of that particular all the greater value to that particular node and sum those value with that particular node and replace that value at that place. So this is our binary search tree. So the greatest value would be lying on the rightmost end and it is 8 in this particular case, so the 8 remains 8. Now I will track back here, so it's 8 plus 7 15. Good. And 15 plus 6 become 21, and this is 5, so 26, and this was 4, so and so on, so on. We will increase the value as per the number of greater nodes that particular node. So the first solution that comes to my mind for this particular question is that if I traverse a tree once, if I completely traverse a tree of once, I do a BFS DFS and store all the node value in an array and then just sort that array. I need to find a value. I will find the upper bound of that particular value. So as for the one, it would be something value like it would be from 2. So from all the values from 2 to so onwards to 8, we have all the values from 2 to 8 plus 1 because that would be the upper bound. So I will just sum all those values from 2 to 8 plus 1 and replace the value at 1, and can do similar thing for each node. So I just need to do a BFS and then I can store all the values in an array. I can sort that array. I can just do a in order traversal. Even I will just do an in order traversal. Everything will be stored in array and a sorted array, and then I will go node by node, find the upper bound of that particular value in the array, and then just sum that particular values. That is the first solution that has come to my mind. Comes to implementation part, I don't think it's pretty tough as implementation. But the particular thing is, since we are having a binary search tree, then storing it an array, is good, but we would be doing some extra complexity work. We would be manually searching every time for each node. Now, what can be the number of nodes? So the number of nodes in the tree can lie in the range of 1 to 100. So there can be 100 nodes, and doing binary search for hundreds of nodes in a particular tree would be not that great of a solution. So there's no way to copy paste this image in this particular thing. That's the biggest issue. So when we have 416, let's just try to make this 416 and 0257 0257. Then we have 3 and 8. There's one more node, and there's one more node, that is 3 and 8. Oh, now to remember the values, but I know that this would be the maximum value in my whole particular tree. So its value will be not replaced. Okay, that's good. So since its value will be not replaced, it would remain same. Its value will be the addition of this value. Good. This value would be the addition of these both values. Good. This particular node that is on my left, it would be holding the sum of this value also. So it's kind of like this, goes like this. And this particular root node, okay, so all these value on this particular side would be greater than my root node. So this value sum plus this value sum. So all these value that was sum of till here will be added this, and then in so on case all these value will be added here, and then this is the smallest value. So all the particular nodes of the tree will be added here. So I just don't need to add the values from this root node, but I will also take values from here and here and here, and then those value will be also added to here. So in that particular case of scenario, I need to move here first. I mean to say, I just need to go here first, add these value, because I don't need to add these particular this node value to this node. It's a right child or left child? Let me see. It's a right child, so 2 and 1 value will be added. What value will need to add? The root of binary search tree convert into every key of the original key plus the sum of all greater key. Yes. So for this particular 3 node, this is the node. I don't need these 3 values because these are smaller than this. Even this particular value might be no, this no, not this, because it's the root of the tree. These 3 value will be not added to this. Okay, so since these 3 value will be not being added to my root node child of this particular part, so what I can say is I'm basically doing a recursion. I go from the rightmost to its previous, because it would be smaller from my right node. I would add the value here. Good. And it was there was this previous node like this, so its value will be also added. So these two will be added to this particular node. Now there's this left node. Now for this left node, I need to add these both values plus this value to this left node, and then pass forward this to the root node, that is here, as complete sum. Okay, so technically what I'm doing is I'm going here, I'm saying are you the rightmost child of this tree, and it says no. So then I go here, and it then again says are you the rightmost child of this tree, and it says no. And then it goes again here and asks are you the rightmost child of this particular tree, and it says yes. Since it's yes, and it is the rightmost child of this particular tree, so the case becomes is that no value would be added to this. It would remain 8 as 8. Okay. Now what I can do is I need to pass this value to the parent of this tree, right? Now if I have a return type something like return, so what I would be returning would be return 8. Okay, I have just returned 8. I have returned 8 to the parent node. Now there's no left node for this. But before I go to left, because the left value could be smaller than this particular node because it's a binary search tree. So I need to add this value of 8 to this particular node first, and then I need to add the combined value to the left. So it's kind of get this return, adds its value plus the return value of this 8, and then again go here and the left, and it will not directly add in the left, it will again go to the rightmost particular part first, because in the right side it will go, and then do that particular adding some. It's becoming confusing here. If I go here, this is my left. Okay, good. Now this is my left. I know these value are bigger than my left. That's well and good. But since it's a binary search tree, this value will be also greater than my left. I don't need this left to be added to this, but I need this to be added to my left. So what I will do, can call, I can go to the right, and store the sum. How can I store the sum? So I can take the sum as initially 0. I will go to the rightmost and increase my sum to 8 and replace this particular node with the sum 8. Okay, now it will return back. Just a second. Here is. So there's this node and there was this node. Okay, so what I need to do, there was this 8. I can keep a sum when I reach the rightmost or end or the leaf of that particular traversal. I will add that value, replace the value at here at 8, then I go back and I do the sum here. And at the same time, what I will do, since it's a bigger node, I know that would be a bigger node. What I need to do is sum this particular value, that is whatever value would be, let's it be 7, then it would become 15. I replace this value with 15, and now my sum is also changed to 15, because this is the sum that I need to forward to the left child. All the nodes that would be here, 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 all the tree in that particular case, and all this tree, whatever the value is here, it would be smaller than this value and this value. So there's no case in that particular scenario where this value does not needs to be added. So I know that this value needs to be added. So I will pass this 15 to the left. But to the left, I will not just directly go to the left and just add this 15. In this left, I will again go to the extreme right and then add this 15 to the extreme right, and then revert back from that extreme right and then take the increase sum to this, because this would be a smaller value, this is a greater value, and then I revert back and then I reach here this value. Even when it was a left child, it was a right child of a right side tree, so its value is greater than this tree. So this particular node is greater than my root node. So its value, this value, and all this particular value needs to be added to my tree. So that value would be added to my root node. Some would be increased again. Now I will go in this particular side, then go again rightmost, add the value of the rightmost, revert back, add the value of the previous parent of the right, and keep doing the same until and unless my whole tree is traversed. So what I can do is write a simple recursive question for solution for this. If I go like this, let's just say I write a void type called solve. I just need to pass my tree node. That is my root. I'm initially at my root. I can declare sum outside the, so sum is 0. Now if not root, then just do nothing, that is return do nothing. Else solve root right, go till the extreme right, some value would be root val, and now what I need to do is root val needs to be replaced by the sum val. Now when I replace it with the sum val, so at this particular case, okay, so just a second, yes, this. So at this particular scenario, I've had this 8. I've just added the value to the 8. I've reached 7. I've added 7. Now my case has become 15. My sum is 15 right now. So with sum 15, now I will go to the left. And since when I reach the left, this is the case, I reach the left, the my left also, what I will be happening is that I again call the solve from here, from root left. Now what will happen is that this root left will again go there. It will go to its right, solve right, sum the value of the right, does not call the sum the value of right immediately. Go to the rightmost of this particular left child. So this, we can say, this is a tree. You can say this is a tree, and we have right, right. Okay, this much right, isn't it? So I will go till the most right of this, add this to my sum, and then I will revert back to the previous node, and then this will again happen here. And when I read this value is added. Now the same will happen for its left child. So this is the kind of solution that I have planned to solve with this. I need to do, okay, it's just sum 0. I think it's wrong. Well, it's globally declared, so sum 0 would be the initial value that is initialized there, but not an issue. Let's just name it solve, call it for the root, and just return the sum. Let's see whether this solution works or not. And this issue, what is the issue? Return sum. Cannot initialize an object of type 2 node. Okay, what is the issue? Was sum supposed to be 0 that I missed? Da, 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 da. Return sum. What is the issue? Is what is the issue? For the solve, while 3 node root, if not root return, that's current root is 30. Solves sum plus, we'll do the root val. Root val will be sum. Then I will solve again for the root left. That is all well good. Sum value would be 0. Then I call my solve for the root and I return the sum. What is the issue, boy? What is the issue? We can't have a solution that works in once, because that will just pure mockery of the system. That's why just LeetCode like to mess with us. Kind of. Okay, please solve this particular solution. If I have submitted this solution, why I've submitted this solution? I didn't want it to submit this solution. I didn't ask to submit this solution. BST to GST, and this particular solution is messing with me. So what I will do is do nothing. I'll just eat a 5 star and do nothing. So just a thing. Is this particular sum is causing issue? Let's pass sum 0 and comma sum, and I will return the sum, and it will take int @sum. Okay, now let's see what happens. Again, submit button. This submit and run button should be separately there. And now again I have some messed up issue. Void store, and okay, there's no comma, and it's, I know this is fucked up. Okay, let's see if it works this time. Again it doesn't work. Okay, I have not called the sum here and here. Call the sum here, and I have to also call the sum in this case also. My left leg is almost dead. Return sum. What is the issue with the sum? Character cannot initialize return object of type tree node. Okay. So that's what happening. I'm just returning the sum of that particular tree. It just need to return the root of the tree. Okay, that worked. I just was messing the shit up. See whether it works. Yes, it works perfectly fine. So I think the solution is pretty clear. It's a pretty easy solution. So let's just wrap this thing up. Move to our next question, that is find duplicate subtrees. Given the root of a binary tree, return all duplicate subtrees. For each kind of duplicate subtrees, you only need to return the root node of any one of them. Two trees are duplicate if they have same structure with the same node value. Okay, same structure with same node value. Okay, great. We have a tree. Let's just make this tree this node, then this node. Okay, good. Looks pretty crap. And this one more. Okay. And there's this case. This is one. There's two three. What is 2, 3 add 3? What is this outputting for this? Given the root of a binary tree, return all the duplicate subtrees. For each kind of duplicate subtree, you only need to return the root node of any one of them. Two subtrees are duplicate if they have the same structure with the same node value. 1 is returned, so only 1 is returned. 2 3 is returned because 2 is also a node. 3 is also 2 3. That's returning the complete tree 2 comma 4 and 4 only. 2 comma. Okay, so this is the 3 3. This is the case 1 1. So we have to take only the leaf node because if that particular case scenario if we're taking, then this 2 4 is the answer we are taking. We are taking this 4 4 as answer, but we are not taking this 2 2 as answer because we don't need this 2 2. So what we are saying is, given the root of a binary, return all the duplicate subtrees. For each kind of duplicate subtrees, you only need to return the root node of any one of them. Two subtrees are duplicate if they have the same structure with the same node values. Okay, these two nodes, why are they not same? To say if the 3 3 node are same, then why does the 2 2 node are not same in this case? But if the two nodes we are just if we just end up counting of the number of nodes, then it would become problematic. Why? Because it's kind of like if there are three two nodes. If I count the value, then it would become a wrong solution. If I take 3 3, the structure is same. 2 3 has the same structure, but these two don't have a same structure. Why? This is the left child of the root node. This is the right child of the root node. So the structure is completely different. But in this particular case, you have 1 1. This is the left child. This is the right child, and we say the structure is shape pretty messed up. We have 2 2, we have 4 4, they are the same structure. Now this 2 4 has the same structure, and this 2 2 should also have the same structure because it is a right node of a particular node, and this is also a right node of a left node of a particular node, because they don't have a same parent. These two have a same parent. So let's just leave it for here just now. For that particular scenario, just leave this out. And we just focus on the question. This is not a node, so we'll think of it as later thing. So currently I have this particular node. We have some value xy here. That is similar to the value xy here. Okay. And I need to find whether these two structures are same. And if these two structures are same, then what I need to do is add these particular values to my array, that these two were the same kind of structure, and I just found these answers. Now this particular thing sounds pretty intriguing, but it is not that intriguing. because this particular node structure, this 2 is causing confusion for me. Because if these three are we adding to the structure, then these two should be also added. This 2, 3 is a separate case. These three are separate case. Then these two should be also a separate case. We have 1, 1 as a separate case, but why we are not having these 2, 2, 2 as a separate case? Sometime there, I think there should be someone sitting from LeetCode side to explain these kind of scenarios, uh, these kind of cases where why these two are not same. Okay, so I am having a root node and this kind of structure. I can't just directly guess this particular node that these node would be same. Now this happened to be here. There could be a larger tree, and these two be might be extreme left or extreme right, but the structure turns out to be same. So I can't just traverse the whole tree and take this particular node. And for there's a question that is we have to check the whether the linked list exists in the tree or not. So it's kind of similar case scenario that I will take this structure as a linked list, not a linked list. I will have this structure and then I will go to every node and then I will compare to this. Now this comparison for the brute force approach would be something that would be bizarre to even give in an interview, because this kind of approach is total crap. This is a total crap approach because we can't just take every node. Because when I say take a node, I am talking about this node structure, I'm talking about this node structure. Apart from these row node in this structure, I'm talking this structure, this complete structure. So you can see there are so many solutions for this particular only three nodes. And then when you are talking about how many nodes can be there can be around a number of nodes in the tree can range from 1 to 5,000. Then it's a bizarre, bizarre solution. So that would be a very, very bizarre solution. So that is not a good solution. So let's think for a minute. We have a tree. I need to store this thing. That's one thing is clear. I need to store for future reference. Now, how I would store that's the issue, and how I'll store the structure, the thing. Okay, I have left. I have right. What is the particular thing next? So, what is this? This is a null node, and here also this is a null node. What I need to do is be holding this structure and I need to hold this structure. How can I hold on to this structure? I can store these two nodes in a map. Okay, so if I create a map, then I will just store like this root and root left. No, this particular thing would be pretty grand. So it's like I'm saying like storing root left, but how will I store this in the map also? If I have root left, I can just add the values like root plus root left. If I just convert it into a linked list kind of thing, now head in next pointer or I just push it in an array. So I can push it in an array. That's the thing. I can push it in an array. I can have a root and can have the left kid of that root in the array. And the right kid of that node in the array, so I can have a map and it will be having an array and it will hold the frequency of that particular array, and I will just compare. So every time I just find a particular node that I think, I will just try to find this array again. But that really doesn't is a good approach, because how will we deal with this kind of scenario, checking whether the values of that particular array are same true or not, because I will need to traverse every value of that particular array. So that will become a hectic case. So instead of an array, what if I have a string? To say I just need to store the value, right? So I can just store the value. I don't need to store the node. I can just store the root val plus the left, yeah, plus the right. So this is a particular node. I can have the left. This is my left, and for right, the right does not exist. So I can just say n for this particular case of scenario, that if the child does not exist, just put a r. So this would become something like, what is the case here? It's like 2 3. It would become 2 3, and it is null. And now this is in map. I can just directly compare and fetch the value in order of 1, and then I can just compare it. That would be pretty good. But I also need to push the value. I need to push the value of the root only, right? I only need to push the value of root only. Uh, okay, so since I need to push the value of root only, it's pretty easy. But what about the depth trees? There could be a tree structure like this, and I have a tree structure like this. So what? So firstly, what I will do is I will try to go to the last node. The recursion, I will try to go till the last node. I will create a string for this particular node. So the string for this would be something like, let's say 8 is there, and since there is no right child, so it's null, and there is no left child, so it's also null, and this is 8 null null. And now similarly there would be, let's say there's 7 here, then it's 7 null and null. This is a string for the scenario base. So this is a string. Now this is a string, this is a string, and these string are returned here. It is a 6. So I make it like 6, and then there's this 8. This is null, and then there's null, and then there's 7, and then there's null, and then so on. So it would be quite a long string, would be formed for many solutions. But since we are dealing with this kind of case, we can easily store all these kind of values in our string. Or what we can do in future is that, since the strings are so big, what if I just replace this null with some -1 and 8 dash -1 and that 6? I can encode this value into a binary value, for binary representation, and store that particular binary representation as my answer. So we won't overflow the memory or kind of situation. But let's see how much we have. We have 1 to 1 value, and the node value will 9. So I don't think it would overflow the memory for this particular case or scenario. So let's try to code this, and while coding we'll try to think the further approach of the solution. So what I need to return is a string called solve, and it will have the tree node root, and I just need to pass the root, right? No, I need another thing, that is unordered map. That will hold my string for my called MP. And yes, I also need a vector that will store my answer. So vector that will hold tree node, and I will call it as result. Okay, apart from this, I don't think that I need anything, and if I will need anything, then I will add it later. So if not root, I have reached the leaf node, then just simply return a null string. Okay, good. I've returned a null string. Now I need to do is string temp. That would be to in my root val. Currently root val is not added. It would be added, but right now it is not added. I will call the solve again for the root left, and similarly I will call the solve. Okay, so I will call the solve again for the right side also. So I will call it for the my right side also. Okay, I called it for my right side also, my left side, and my. So after doing so, I have a new string that is temp. If my MP is already having this string, mp.temp is already there, greater than or equal to 1, then do this result dot push back the root, because it's a valid state scenario, so it's a root, so it is a valid case. Now what I will do is increase the mp temp and just return this particular temp that I have created. So this is the case. If there is no node, then just return null. Call the recursion for the both left and right. These will build the subtree strings. Okay, if the string is already in map, then in that case we have a valid subtree. I need to call this function from here also, unordered map. We have string comma int, call it mp. We have a vector that is holding our tree node, and we call it result. And then I call solve with the root comma mp comma result, and then just return result. Okay, this is a structure, this is a code. Let's see whether it's run or not. Okay, there's compilation error. Okay, I'm not get it well. Okay, there's again this error. What's the issue? False, all rightfully right. What's the issue? Okay, I've just called solve here, not pass the MPN result. In that case, I've done MPN result here also. Okay, pass MPN result, MPN result. Let's see, there is one wrong case answer. What is the issue? Okay, so 4 is coming again and again. Why 4 is coming again and again? We have 2 comma 4, we have 4. Everything is right, but this 4 is extra. Why? Okay, so I think what I'm causing the issue is that is this MP temp greater than equal to 1. Why? Because if this is a kind of thing that this 4 is more than twice, so that kind of thing. If string counts once, let's try this. If string counts 1, then only we will push it in the map. Yes, this was causing the issue. Try to submit it. Okay. Okay, we have solved this. Now, since we have solved this particular part of solutions, now what I need to work on is some more problems that I think I should be working on. Let's see that there are some valid more tree problems that I need to do. Well, I'm currently busting my ass on tree. I'll move to DP next week and I will completely work on DP for the next week. But for this week, I am sticking to trees. And there's some tree structure that is something that builds the recursion well, so it will definitely help me in the DP part also. So that's the particular thing. Okay, so should we go for some easy problems also? Well, we can go for easy problems. Some 2, Possum, like kind of problem that should I solve? Should I go for easy? Should I go for hard? What kind of problem I should go for? Binary tree, search tree, I filter, binary tree, right side view, invert binary tree, kth smallest element NBST, lowest common ancestor of a binary search tree, lowest common ancestor binary tree paths. These are easy, these are log problems. House robber, sum of left leaves, awesome 3, delete node in VST, find mode and binary search tree, find mode, convert VST to greater tree. I think this is the same problem that I just solved. Diameter binary tree field. What kind of problem should I be solving? Construct string from tree. Average of labels in binary tree. I can just do a label data traverse and it's quite clear from the name. Da, 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 da. Should we be doing? We're just ending today. I'm pretty tired already. Let us and research tree, validate my research tree, same tree. Okay, same tree. Should I go for some easy problem? These are pretty easy problems. Should I go for them? That's the thing. Let's solve the same three problems, easy problems over this kind of thing. Okay, so we have a tree. What is the kind of scenario we have? We have a tree given the root of binary tree, P and Q. Write a function to check if they are the same or not. Two binary tree are considered the same if they are structurally identical and the nodes have the same value. So 1, 2, 2, 3. So this is structurally. Oh, this spelling is pretty tough. Let me try it in my British accent. Structurally identical and the nodes have the same value. Okay, so I have 1, 1, 2, 3, and this is a kind of thing. This is a tree. I have 1, 1. That's good, but this is a left child. This is a right child. So that kind of scenario falls. So I can just pretty easily solve this thing. I just think if root. Okay, so this if p dash val is equal to q dash val. Okay, sorry, and is what is the function name? Same tree p dash left and q dash left and is same tree p dash right, comma q dash right. So if the p value is equal to the q value, then I just go to the left value and do the same recursion and ask whether the value are same, and then I go to the right and ask to the also same. Let's see whether this works or not. There is compilation error. What is the compilation error? Okay, what is the compilation error? Saying is same tree. Have I written the spelling wrong? Okay, okay, I'm not returning anything, right? That was the issue. Return, sorry. Just return. Runtime error. Why? Runtime error member X is within null pointers of type. Okay, so I have not checked the null case. Okay, since I have not checked the null case, why not check it? If p, okay, so if I don't have p, so there's this 2 and there's this 2. If there's no p and there's a node here, then it is structurally different, right? The structure is not same in these cases. So if this is null and this is not null, that would be a false case. But if this is null and this is also null, and there's this right child that is null and this is this right child that is null, that would be same. So if it is not, if it is null, and then this should also be null in Q, then I should return true. If P is null and Q is not null, or there's a case that P is null and Q is not null, then I would just return false. Let's try to run this. Da 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 da. Ah, this got accepted. Just increasing my kill count on the LeetCode platform so that recruiters say, oh, you have solved so many problems, right? No, that's not the case. It was a pretty easy problem. Let's see if we have some similar topics or kind of problems. Topic tree, depth for search, breadth for search, whatever. We solved one more problem. So far, we have solved 6 problems, and I think let's solve this symmetric tree also. Since we are increasing our kill count, I'll just not increase it here also. Given the root of a binary tree, check whether it is a mirror of itself or not. Okay, so I need to check whether the tree is a mirror of itself or not. So I have to. So it's the same code. It's the same code. It's just the same code. I just need to don't need to check the root node. What I can do is, where is this tree? Where is this same tree? Yes, it is here. So this is the same tree. Okay, this is my same tree code. I'll do is copy this, just paste it here. Same tree, and I need to do return is same tree root left, comma root right. Let's see whether my thinking works or not. Okay, so it has failed in both of these cases. Why? I go there, I do this. The same questions, same code. Why it's not working? Why it's not working? Why it's not working? Where the okay, this structure p left. This is the p left, and this is This is my p value, this is my q value, this is fast. Okay, good. Now this is 3 and this is 3. Okay, so there's this issue. I just passed this. I need to change this. This should be the right and this should be the left because we are dealing with the mirror thing. So since it's a mirror thing, the left would be right and the right would be left. So I was just messing that up. Okay, let's try to submit this. It was the same question. I don't think it's even different from the particular question. Okay, aura farming plus 900. Okay, now since we have solved two more easy problems, let's see what our kill counts looks like. Okay, we have 8 on our kill count. Right now, what we need to do next is something. Mandatory right side view, count complete tree nodes, uh, invert binary tree, Kth smallest element in BST. Let's try this. What is this question that says find the Kth smallest element in the BST? Gosh. Hmm. Let's take a washroom break and let's come back to the problem. Kth smallest element in BST. Given the root of a binary search tree and integer k, return the kth smallest value of all values in the trees. Kth smallest value, all values in the trees. Well, that's pretty interesting. We need to find the kth smallest value, all the values in the tree. That's pretty interesting. Mhm. We have 3, 1, 4, 2. What I can do is just simply do a in order traversal on this. Just get that value directly from there. That would be my in order traversal solution. Because since it's a binary search tree, that would be storing the value in a sorted order. And since I would be having the values in a sorted order, I can just directly find the kth smallest value. I can even push that in a priority queue. That's pretty good, but the issue lies is that I will be doing a in order traversal using an extra memory for storing that in order traversal, and then I will need to find the kth value. I just can access in order one, but why do so? How can I do this in a better way? That's the case. Okay, kth smallest value in a BSD. How can I solve this question in a better way? In order traversal is good, it's definitely good. But why go for in order traversal? Is there no better solution for this? Is there no better solution for this? Let's move to the uh, drawing board. Let's try to solve this. We have 3, 1, 4, 2, right? We have 3, we have 1, we have 4, and what is the next one? This is 2. Now I know that this 2 is the smallest, this 1 is the second smallest, then there's this 3, and then there's 4. But what if I change the structure of this tree? Let it be same, almost same. I have this node, I have this node, this node. I have these two nodes. Now this time this is 3, this is 2. Okay, nah, not this. Drawing this on this board, I need to buy a new this tab and pen thing. Okay, so I have this node and I can have these two nodes first. Now let's say this is 7 and this is 6. Now this is 6. Now that would be a ouch factor. So if I made it as 8, this is as 6, this is as 7, and this is as 5. Now the kth, let's say I need the third. So my smallest answer is this 5. That is for sure. Now I come back to is this 6. This is my second smallest. Now if I go to the parent back, that is the root, then I will miss this 7 out. So I need to this 7 also. So for that case, that is why I was doing an in-order traversal on this particular case. We'll do this, and then I will go here to the root, push the root, and then I go to the right, then I store the right, and that would be in-order traversal. That would be great, but I will have to store it somewhere. That's the thing that I would need to store it somewhere. So I think the in-order traversal solution is pretty good, right? Even if I go anywhere, is there any better way to solve this? Is there any better way to solve this? When I go here, I decrease my k count. Okay, so when I go here, my k was is nothing. Then I return back, but when I have this 5, I decrease my k. Now when I come to this 6, it says the k is 2. Okay, now the k is 2. Now I come to 6, it will also decrease k by 1, and now this k is passed here to this 7. This 7 says now since k has come to me and k is equal to 1, because we are not taking this value, we are taking one base indexing, so that's why there's this confusion. We have taken zero base indexing to have been better, or zero base numbering, we can say 0 1 2. So when I come here, k becomes 0. So since my k is 0 at this particular index or particular node, then it's my solution, right? So every time I go to the right, I just need to do this. Okay, that's also a thing. Okay, so that's also a thing. Mm, so yes, if I don't store up the values, I can just do it pretty easily, right? Just need to decrease the k. Every time I do this, I will just need to decrease the k. So I will do the in order traversal, but I will not store the value. Instead, I will decrease my k, or I can just increase the counts to match that k. That would be pretty good. Then write when in order, IORDER. Sorry for the spelling confusion. I will take the tree node. I have the int, that is my k, and then I will have count. Now I have count at this. What I need to do is, given the root of a binary search and integer k, return the kth smallest of all the values. Okay, so kth smallest. I will need to hold my result somewhere. Let's say I will be holding it my result variable. Okay, now let's move. If not root, then cult classic, just say return. Do nothing, just return from that particular point. Return. Good. Now this is simple. I will do in order to the left. ORDER, in order root left k count is increased or not. I will increase only the count just like when I reach here. So when I reach here, then I will only increase the count. I will not increase the count every time I go down because that will mess up my logic because I am at root. I increase the count and then I go left. That's messed up. I don't need that. I'm at the root. I will go till the leftmost node first and then I will increase my count or decrease my key. So this is the count would remain same and I will just pass the result also. Now what I will do is that now I will increase my count. Now if my count is equal to k, what I do is result is equal to my root val, whatever the value is here currently, and just return because there is nothing more further to do. Else I have to do an in order root right, okay, k comma count comma result. That's pretty good. Now what I need to do is just I need to call this particular solution and count is equal to 0 and result equal to minus 1. Okay, so result is minus 1 and I just need to do is in order from my root with k with my count and with my result and just return result. Now let's see whether it's run or not. Let's see whether it works or not. Let's see whether it works or not. Okay, let's try this to submitting. Let's try to submit this. Okay, so it works. Okay, so let's end the today's video. We were able to solve four question. I will not count the easy question as a question because they were pretty easy. But for tomorrow, I will choose certainly some hard questions, extremely hard questions. I would say that would take good brainstorming, good designing skills, kind of sketching. It will, yeah, Picasso, and that would be enough. Okay, so let's